In the previous video, we did kind of a reverse analysis of spanning tree protocol. We've looked at why do we need layer 2 flooding in general and what could some alternatives to spanning tree have been. And this allowed us to kind of do this reverse proofing of that, yeah, spanning tree really was the right solution at the time for preventing layer 2 loops. So in this video, we're going to look more in depth at spanning tree, the concept of spanning tree in terms of math, and then look at the spanning tree algorithm at a high level. So we're not going to go into real depth here, but just get a high level understanding of how the algorithm works. From there, we'll look at different versions of spanning tree, so rapid spanning tree and multiple spanning tree. So we'll start here with spanning tree with graph theory, and if you're not familiar with graph theory, it's very quick to get you up to speed in terms of the amount of knowledge we need to explain spanning tree. You may actually be familiar with this from OSPF training, like Nick Russo talked a lot about graph theory in terms of OSPF. So graph theory is just a mathematical study in which objects are linked together. It's like a way to represent objects and the links between them. So this here is a graph, this image right here. And to us with networking, it looks a lot like just like a topology of routers and links between them. And it actually doesn't really hurt to think of it that way. But in graph theory, we call a node a vertex. So a plural of it is vertices. Vertices is the plural of vertex. And the links between vertices are called edges. And in graph theory, an edge connects two and exactly two vertices together. So this is really all we need to know to start understanding spanning tree. So with graph theory, a spanning tree is a subset of the edges that essentially touch every single vertex in the graph without forming any cycles. And in graph theory, a cycle is like a term for a loop. So in this example, we've got this grid of 16 vertices and edges connecting them. And they've selected a spanning tree here consisting of the blue edges. So you can see that this tree that they've selected that's produced by selecting these blue edges touches every single vertex in the graph, and it doesn't form any loops, any cycles. Like if we connect this one here, if we make it blue, that would form a cycle. So that would be incorrect. That would no longer be a spanning tree. So this is a concept that already existed before Radia Perlman invented spanning tree protocol. You know, she already knew about this. I'm sure she most likely studied this in college. It's a concept that applies to graph theory that wasn't invented by Radia, but what she did invent was the algorithm of creating, or of finding a spanning tree, producing a spanning tree for the purpose of preventing layer 2 loops. So there's another more specific type of spanning tree that we should understand as well, which is a minimum spanning tree. And to understand this, we also have to kind of go back to graph theory fundamentals, which I didn't explain, which is that in graph theory, edges can have weights. And to us, that looks like cost, like link costs. And we really can think of this like topology of OSPF routers, and this is the OSPF cost on each link. It pretty much is like that. But with graph theory, we say the edge has a weight, usually, instead of a cost. So a minimum spanning tree is just the one spanning tree, or maybe there's multiple with the same weight, total weight, but it's the one spanning tree with the lowest total weight. So to find this, we could, for this graph, we could calculate every single spanning tree, and for every spanning tree, we could add up all the weights of every edge in that spanning tree to get a total weight for that spanning tree. Then we just pick the one that has the lowest total weight, and that's our minimum spanning tree. That's the spanning tree that uses the the minimizes the weight, the cost. So this is starting to get close to what we're familiar with spanning tree protocol, because with spanning tree protocol, the links have cost, and we minimize that cost to the root. But notice that in the spanning tree and the minimum spanning tree article, we never mention anything about a root. We don't need a root to find a spanning tree. So it's interesting that we have a root in spanning tree protocol, and we'll get to why that is in a minute. But having a root affects the finding the minimum weight if we find the minimum weight in relation to the root. So I'll give you an example. Like, let's say we make this node the root. Well, now the minimum spanning tree is not the most optimal spanning tree for minimizing cost to the root from in respect to the root, because this node here has an edge that has weight 9, but it's not being used. It's being blocked in spanning tree terms. And it's using this path that's a cost of 15. So if we want to minimize cost to the root, that's actually something different. We have to take a spanning tree that minimizes cost to the from a given root. So in my opinion, I call the spanning tree that spanning tree protocol implements a rooted minimum spanning tree, meaning that we calculate the spanning tree from the perspective of a given root, and we try to minimize all of the nodes' cost to that root. And I don't know if that's really an official like math term. I haven't been able to find like something calling spanning tree a rooted minimum spanning tree, but that's something that makes sense to me, and maybe it makes sense to you. It's also interesting to note that spanning trees are useful for much more than just producing loop-free layer 2 topologies. They can be used for real-world applications such as finding the lowest cost of copper to wire up a building. You know, you could say in the building, each outlet is a vertex, and all the possible paths that you can run wire between each outlet and outlets next to it are edges to connecting, exactly two outlets together. And you could minimize the cost of copper by finding the minimum spanning tree. You could have the weight of every edge be the length of the wiring that you would run between that on that edge. So that there's more use cases for spanning trees than just layer 2 spanning tree protocol. So now let's get into why spanning tree protocol has a root. Well, radio programming could have developed a link state algorithm for spanning tree protocol in which all of the switches know the full topology of the layer 2 topology. Like, if this switch here knows the entire topology of all the other switches and all the links between them and the cost between them on each of those links, it can independently calculate the true minimum spanning tree. And all switches could independently calculate a true minimum spanning tree, and maybe they have some tiebreaker criteria for if there's multiple minimum spanning trees. But the problem with this is that as you add more switches to the topology, the memory usage of holding the link state database increases. And one of the requirements to Radio when she was developing this algorithm to solve this problem of layer 2 loops, one of the requirements for this was that that what she developed had a constant memory space. And what that means is that as you add layer 2 switches to this topology, the memory utilization of spanning tree process on each other switch should not start increasing. It should remain constant. And that doesn't mean that it's not linear. That doesn't mean that it can just linearly grow. It really means remain constant, remain 200 bytes. That's your memory usage. And as we add more switches, that memory usage doesn't change. So that's not possible with link state. But she had this very elegant solution, which was to do a distance vector approach. So that because with distance vector, each switch is only storing the best PPDU, or like the best route in terms of distance vector routing terms, that it receives on a port. So that's a constant fixed amount of memory. That's perhaps 60 bytes. And you multiply that by the number of ports a switch has, that's the maximum memory usage that spanning tree protocol process is going to use on that switch. So it's a constant memory space. It's never going to use more than that, no matter if you have 1,000 switches in the layer 2 domain. So in order to build a spanning tree through this distance vector approach, we actually have to have some point in the topology that we call the root, and then calculate lowest cost path to that root. So we say this is the root. The root advertises it's the route to itself, where instead of a prefix like a IP prefix, the route is just the root bridge ID. It says, oh, the cost to this route is 0. And then each switch receives that and adds its own cost to that route advertisement, and it cascades away from the root. And then we build a spanning tree through that. So it's a very elegant solution for achieving constant memory space and doing layer 2 loop prevention. So now let's get into how the spanning tree algorithm works. We kind of touched on it here with how it works with the report and costs and everything. But let's just get a high-level overview. We won't go into super depth because there's lots of spanning tree training material that goes really into depth about the algorithm and the whole process, and we'll go through 20 slides in excruciating detail. And the point of this series of videos is to give you a different perspective, information that you can't find in other training material. So we'll just kind of level set and do a quick overview of the algorithm. So we'll use this simple topology to explain the algorithm. So first, a root bridge is elected, and it's elected through preemption. And there's no way to disable this preemption because it's completely necessary for the algorithm to function correctly. Is that anytime a switch hears a better root bridge ID, it must update its known root bridge ID for the spanning tree instance. So each switch starts out believing that it itself is the root bridge ID. The root bridge originates configuration BPDUs, which say this is the root for the spanning tree instance. And upon hearing a better root bridge, the switch stops originating that. Oh, okay, actually this is the bridge. And that happens iteratively until all switches finally converge and agree that there's one root bridge in this topology. And that's something that the switches don't all have some way to confirm with each other. It's just something that eventually the switches will converge, and through this process of preemption, they will all agree on one single root bridge. Once the root bridge is selected, each switch selects its one best port to that root bridge, the lowest cost port, as the root port. And if there's multiple lowest cost ports, then it goes through a tiebreaker process of perhaps lowest port ID or something like that. So here, this is the root bridge, and these two bridges have selected this port as their root port, the lowest cost port to reach the root bridge. The next step is that on every segment, there must be a designated port that is elected. And the switch with the lowest cost of the root bridge, or if it's a tie, the lowest bridge ID, is the bridge that has the designated port on that segment. So on these two links, the root bridge itself has the best cost to itself, a cost of 0. So it is the owner of the designated port on that segment. So this makes this link fully operational in both directions, right? On this segment, there's can only be one designated port, and one other port is going to be blocked because there's no root port on this segment. So perhaps this bridge has the lower bridge ID. So this port is going to be blocked, and this port is going to be the designated port. And this switch, there's no, mechanism where this switch says, oh, are you going to be the designated port? And this switch says, oh, yeah, I'm going to be. No, it's an algorithm that runs on every bridge individually, where this bridge says, oh, I see that this bridge has the lower bridge ID, so it's going to elect itself as the designated port on the segment, so I'm going to have to block this port. So through these steps, eventually we have a spanning tree topology, where even though this port is forwarding on this link isn't operational because this switch is blocking on that port on that segment. So it's a fairly simple algorithm. It's a very elegant way of finding a minimum rooted spanning tree. And this algorithm also needs some way to handle transitions and changes to the topology, so links going up and down. And it handles this through the mandatory states that a port must participate in before it can go from blocking to forwarding. So to transition from blocking to forwarding, a port must go through these transitional states of listening and learning. And it stays in these states for a fixed amount of time for the forward delay timer, which by default is 15 seconds. So first it goes to the listening period, in which the bridge is allowed to start sending BPDUs on the port, and essentially now it's participating in spanning tree. So this period is just kind of a safety period to ensure that the topology has time to stabilize. Next, it goes through the learning period in which it can learn the source MAC addresses of traffic being received on that port, and it can build its CAM table. So this is another safety period just to reduce mass unknown unicast flooding after topology changes happen. So any convergence event that happens with spanning tree is going to be a minimum of 30 seconds for convergence, because a port that's blocking, in order for it to go up and go forwarding, it's going to have to go through listening and learning. It might additionally have to first age out the BPD that's stored on that port before it can transition to listening and learning, in which case that will be the max age timer that dictates how long that BPU is saved on that port. So it's kind of like a hold time for the BPDU on that port. So the convergence time for spanning tree is anywhere from 30 seconds to 50 seconds. And generally it's like either 30 seconds or it's 50 seconds, not like something random in between. And then on the topic of topology changes, the switches need some way to inform other switches that a topology change has happened. Because if a topology change happens, then switches need to flush out their MAC table entries, because the MAC table entries are hinged on the spanning tree topology, because I've received this source MAC on this port. Well, if the topology changes, this port has gone down, or a port upstream has gone down, so now that source MAC is going to be received on some other port, the switch has to flush out its CAM table entry, because that entry is no longer valid. It's no longer valid that you should send traffic towards that MAC address out that port. It's actually reachable at another port. So if there was no topology change notification mechanism, then you'd have 5 minutes of outage, up to 5 minutes of outage for some hosts on the layer 2 network, which is completely unacceptable. So what happens is that if a topology change happens, which in spanning tree is any port going down or up, a topology change notification is flooded. So in spanning tree, there's only two types of BPDUs. There's a configuration BPDU that the root bridge originates, and there's a topology change notification BPDU, which a switch originates when it has a port go up or down. And that switch will flood it towards the root, and then the root will set a topology change flag in the configuration BPDU to let all switches in the whole topology know that, yeah, topology change has happened. And what the switches do in response to that is they shorten their CAM table timeout value to the forward delay timer. So if there's whatever entries they have, all those entries, if they're greater than 15 seconds, they shorten them all down to 15 seconds. If there's an entry that has a current timeout value of 4 minutes and 30 seconds, it's going to shorten it down to 15 seconds. So this is an optimization as opposed to just completely immediately flushing their whole CAM table. They can just, we'll short it down to 15 seconds so that we're reducing unknown unicast flooding, but we're still making sure that we purge out old entries. And this 15 seconds directly comes from the forward delay timer in terms of how it's used for the listening and learning periods, because we can shorten it down to 15 seconds because a port that's going from down to up is going to have to go through listening and learning for twice the forward delay. So if we just set the CAM table timeout to once the forward delay, then we're perfectly safe of aging out CAM table entries. Okay, so that covers the spanning tree algorithm from a high level. So let's now look at rapid spanning tree. So rapid spanning tree is a new version of spanning tree that, instead of relying on these slow timer-based convergence, it does a explicit handshake mechanism, a synchronization mechanism to converge. So the process is that two switches on a link say what they have for the root bridge ID. So let's say this topology comes up fresh, each switch thinks it's the root bridge. The switch will say, hey, I'm the root bridge. And the other switch says, no, actually, I'm the root bridge. And then the other switch says, oh, yes, I agree, you are the root bridge. It's an explicit acknowledgement. And the other switch can see, okay, yeah, that switch believes I'm the root bridge. So instead of this timer base where we're waiting for listening and learning, we don't have that anymore with rapid spanning tree. We just immediately, we do this kind of conversation between switches to handshake and agree that, yeah, we agree who the root bridge is. So during this process, when a switch detects that there's a better root bridge, it says, I'm the root bridge, and the other switch says, no, actually, I'm the root bridge. So then this switch says, wait, I'm not in sync. There is actually a better root bridge, and it's not what I thought. I have this new information of a better root bridge. So I'm going to set all my other ports to blocking, because this is like a dangerous situation. I don't want to form a loop, um, because all these ports are not in sync anymore. So I'm gonna okay, now we've synchronized on this port. Now I'm gonna go through all these ports and start synchronizing. So the rapid spanning tree synchronization process kind of ends up cascading down because eventually all switches kind of replace the root bridge that they know with the best root bridge, and then that synchronization from the best root bridge is going to kind of cascade down hop by hop through switches away from the root bridge. Um, so this synchronization process is sub-second, and it's why it's kind of hard to get an explicit time value for how fast rapid spanning tree converges, because if all links in the layer 2 topology are like direct links, and a link going down can be directly detected on the switches at layer 1, then synchronization is extremely quick. It's just said to be sub-second, and you can't really get an exact time because it can kind of vary of, how long it takes each handshake to take and how many switches you have in the domain and things like that. But you can assume that it's going to be sub-second. However, it is important to know that rapid spanning tree cannot detect the link being down at layer 2 without at sub-second. So if you have, you know, let's say 3 data centers in a triangle and you're doing layer 2 between them and you're running rapid spanning tree and you think, okay, well, if one link goes down, I'll just get sub-second failure. That's perfect. But then you might have something come in and you get a ticket that says, hey, there was like 5 seconds of outage between these data centers. And you're like, well, that's not right. It's rapid spanning tree converges in sub-second. But you'll come to find that actually what happened was the carrier had an outage on your point-to-point link between 2 data centers, and at layer 1, the ports were up on the handoff equipment for 2 data centers. So rapid spanning tree can't detect that. It just relies on the failure to receive 3 hellos, and the hellos are by default 2 seconds, so it's going to be 6 seconds time to converge. So it's important to know that, because I actually ran into that problem with rapid spanning tree, and it was hard for me to find that information because everything just says, oh, rapid spanning tree converges as sub-second. But you have cases where the link down detection is not at layer 1, and there's no such thing as like running BFD for rapid spanning tree. So it's good to understand what happens if the link failure is not at layer 1. So we understand the synchronization mechanism now, but let's talk about how topology changes work. So in rapid spanning tree, topology changes only happen when a port goes up. And I believe this is kind of an optimization because you can imagine that if like there's some like leaf switch at the very bottom of the topology and a port goes down, the spanning tree topology hasn't changed. It doesn't matter. We don't need to like reconverge and flush cam table entries and stuff. But if a link goes down and then an alternate blocking port needs to now go up, only that port that's going up causes the topology change. So you can basically just say, well, we'll only consider topology changes when ports go up. Okay. The difference with topology changes, though, the other difference, because in spanning tree, port going up or down is a topology change, and rapid spanning tree, only a port going up is a topology change. The other difference is that with spanning tree, the cam table, the action that all switches take upon receiving a topology change notification is that they're going to lower the cam table forward delay timer, or lower the cam table timer to the forward delay time, which is 15 seconds by default. With rapid spanning tree, we're not doing convergence based on these slow timers. We're doing this immediate sub-second convergence based on handshakes. So the cam table just has to be flushed immediately. So this is a little bit of a problem. This can cause some mass unknown unicast flooding, because anytime a port goes up, all the switches just immediately flush the cam tables. All MAC entries are gone, and they just have to completely start fresh, and that requires unknown unicast flooding. The other consideration with this is that port fast is incredibly important with rapid spanning tree. And in my opinion, it's kind of a common misconception, or it's kind of a beginner thing to think, well, what port fast does is it just allows you to bypass listening and learning periods of so that when a user connects their PC, it immediately goes up instead of like waiting 30 seconds. Yes, that is what port fast does. But from a network design perspective and network stability perspective, what's actually more important about port fast is that port fast ports don't create topology change notifications. In rapid spanning tree, port fast ports are also called edge ports. So in rapid spanning tree, if you don't configure port fast ports, then a user port or a server port going up, well, flapping, but the action of going up is what causes the topology change. That causes a topology change notification, and then all switches in that layer 2 main flood or purge all their cam table entries, flush their MAC address table, and now start flooding unknown unicast traffic. So you can imagine if a user port or server port is flapping up and down, it's just causing constant MAC address table flushing, and it's a very negative impact to the layer 2 network. So it's very, very important when using rapid spanning tree to set port fast ports. Also, the other danger of rapid spanning tree, well, this is a little bit more complicated, and you might not fully understand this until we go into more depth about the spanning tree toolkit and why service providers don't want to use rapid spanning tree on their ring topologies, layer 2 topologies. But I'll mention this anyways because we're talking about rapid spanning tree. The other problem is that uplink fast and backbone fast are built into rapid spanning tree because we're doing like a synchronization-based convergence, not timer-based convergence. But the problem with this is that in backbone fast, what happens is that it allows a switch to help another switch from its loss of a root port. So like when a switch loses its root port, it might think, oh, well, now I'm the root. So I'm going to start on this other port, I'm going to start saying, hey, I'm the root. But that other switch can actually help it bypass the max age timer and say, bypass its own max age timer and say, hey, actually, let's just not do this max age thing, this 20-second of timeout. And I still have reachability of the root. You're not the root. You didn't lose, we didn't lose the root in the topology. You just lost your root port. But in order to safely do that, the switch that's helping out what it does is query the whole layer 2 spanning tree topology or the domain and say, hey, actually, before I tell this guy that the root is still alive, is this root still alive? If it is, then okay, yeah, I'm safe to say, hey, actually, you're not the root. The root is still alive. If it might actually get a response that actually, no, that root is gone. You just haven't heard about it yet because you're not directly connected to the root the way this switch you're helping is. Then that switch can also know, oh, okay, actually now the root is gone. So now we just need to like reconverge in spanning tree. So that's backbone fast in spanning tree. But with rapid spanning tree, we don't do that because we're not doing this timer-based convergence. It's just this handshake of, hey, I'm the root. And then the other switch that's helping could either say, no, you're not the root. I still have reachability to the root. Or it could say, well, actually, let me check first before I tell you and see if the root is still alive. Well, with rapid spanning tree, it doesn't check first. There's no root link queries. It just says, no, you're not the root. What I have is that the root is still this. But maybe that root is actually gone. And that can cause a race condition in rapid spanning tree. And we'll look at that more in depth later. So yeah, that's rapid spanning tree. And now let's take a look at multiple spanning tree. And before we look at multiple spanning tree, we should mention that Cisco created like per VLAN spanning trees. So per VLAN spanning tree or per VLAN rapid spanning tree. What that means is just that you do a separate spanning tree instance for every VLAN. This gives you the ability to actually fully like use a link. Like, well, let's say in this topology there was 100 VLANs. If we just do if we make this the root bridge for all VLANs, then this link is just not going to be used at all. But what we could do if we wanted to have some traffic go over this link, just kind of share bandwidth, we could say, okay, this is the root for VLANs 1 through 50, and this is the root for VLANs 51 through 100. That way, this link would be used for VLANs 51 through 100, and you'd be able to send traffic on all links. The problem with this is that it's a lot of spanning tree instances to calculate and maintain, have a configuration BPDU sent every 2 seconds. Imagine if you have thousands of VLANs, that's thousands of configuration BPDUs, and each one is sent every 2 seconds. If there's topology change notifications, you might have to send 1,000 for them because there's a topology change on a trunk board and all this kind of stuff. It gets messy with that many instances. And you would kind of think, why? Why do I have so many instances when actually I only need 2? I only need one where this is the root bridge, I need one where that's the root bridge. Well, this is what multiple spanning tree allows you to do. It allows you to say, I've got one instance where this is the root, I've got one instance where this is the root, and I'm mapping VLANs 1 through 50 on this instance. I'm mapping VLANs 51 through 100 on this instance. So it only creates, you only have 2 instances here. And it uses rapid spanning tree for each instance, but it's just this way of saying which VLANs are you mapping to which instance. And because there's no like control plane protocol for this where switches like advertise, one switch advertises the database, mapping database or something, you just have to have all switches agree on this. So you have to configure all switches and configure them with 3 things. So we can actually go to this article which has this. So they have to have the same configuration name, which is kind of like the domain name for this MST region. They have to have the same configuration revision number, just some arbitrary number. And then they have to have the same VLAN to instance mapping digest. So this is just a way to communicate whether switches have the same VLAN to instance mapping database. They configure on each switch you individually configure, okay, VLAN 1 through 50 is instance 1, and VLAN 51 through 100 is instance 2. The switch produces a digest of this to kind of more compactly communicate this information, and then if switches have the same digest, then you can assume that they have the same VLAN to instance mapping database. So if all 3 of these items match on a BPD that a switch receives, then a switch considers that switch as belonging to the same MST region. So with multiple spanning tree, you have 16 possible instances. One is a required common instance, which is instance number 0. And that required instance is because it allows the region to interwork with spanning tree instances outside of the MST region. So it allows this backwards compatibility. If it allows the MST region to connect to another, like a legacy spanning tree domain, and it uses that common IST for the BPD that it sends with the legacy spanning tree domain. And the common IST makes the MST region appear as like one switch. So if we look here, this is like the MST region, and this is like a legacy spanning tree domain. And to the legacy spanning tree domain, it kind of looks like the MST region is just one switch, because these switches and this switch appear as the same bridge ID. So that's really all there is to multiple spanning tree. There is one kind of interesting thing to notice, that if this legacy spanning tree domain is running per VLAN, the switch can actually detect this, and it will just replicate the common instance BPDU for every VLAN that it detects, on that trunk port. And there's some kind of there's some gotchas with using MST, like so by default, VLANs are mapped to the common instance. If you don't map them to any instance, then usually you explicitly map all your VLANs to other instances besides the common instance. So there's some problems that can happen. Like, for example, here, somebody put VLAN 10 on instance 0. They left it on the default instance 0, and they put VLAN 20 on instance 1. But what happened is, actually, for instance 0 is always on all links. And this link was blocked on instance 0, so now VLAN 10 is not working. There's little problems that can happen with that, and there's some complexities with the MST region interworking with the spanning tree on the connected next to it, because there's some problems where, what happens if you're doing per VLAN spanning tree, but like the MST region is root for some VLANs, and the legacy spanning tree domain is root for other VLANs. That's not going to work, because the MST region, it just has this one common IST BPD that's replicating for all the VLANs. So you get into these kind of gotchas and things that can trip you up with MST, but the main point with MST is just that it allows you to create separate instances and map multiple VLANs to one instance. So I think that covers it for this video. In the next video, we'll look at the spanning tree toolkit, all the things like port fast, uplink fast, loop guard, root guard, all that sort of stuff. And then we'll look at what are some problems with spanning tree, like, what problems, do service providers in particular have with it. And then finally after that, we'll get into the real service provider specific stuff.